The topic of these papers, as the name of the talk implies, is this thing called gradient flow. And gradient flow is a type of monotonicity theorem for these RG flows. As I'm sure you're well aware, since the C theorem by Zimological about 50 years ago, there's been a veritable explosion of these types of theorems in a variety of different theories and different dimensions, the A theorem in 4 dimensions, the F theorem in 3 dimensions, and more recently there's been a lot of work in defects with the G theorem, the B theorem, and that sort of thing. But the basic idea for all of these theorems starts with a sort of heuristic picture that we like to draw of a Q of t living on some RG flow between some UV-CFT and some IR low energy CFT. But it's a sort of very naive picture. I mean, in principle, the renormalization of these theories is governed by some sort of dynamical system, and these systems can have much more complicated behavior as the solutions. You can imagine that you could have a Q of t that lives on some sort of RG circle, that you get some closed loop, or even more exotic behavior. You can have ergodic behavior where your RG flow would go throughout an entire region while never finding a fixed point. And monotonicity theorems allow us to sort of zoom in on this picture, not only being a heuristic one, but really being a sort of correct one. So the idea is that we want to constrain the behavior of these sorts of flows by defining a quantity which is monotonic. So these come in a variety of flavors. We can demand weak monotonicity, where the quantity we define, A, is defined only at the endpoints, such that its value in the IR is always less than or equal to the value up here in the UV. So somehow, as you've gone down this RG flow, you've integrated states out, and the number of states you have is decreased. Somehow this monotonic quantity, which for this talk I'll just call A, counts the number of states. But this condition, this weak monotonicity, doesn't really zoom in that much on this picture because it only tells you stuff about the endpoints. It doesn't tell you anything about the behavior of the actual RG flow itself, anything in this middle here. And so to do that, we want to go make this condition a bit stronger and demand strong monotonicity, where this A is now a function of some RG parameter mu, RG scale. It's defined for the entire flow such that the derivative is always negative, so that in the IR it decreases. And this really does zoom in on this picture. This immediately you see sort of removes a lot of this exotic behavior that you might be worried about in renormalization. Namely, if you try to have some sort of closed cycle, some limit cycle for a QFT, you see that it would need to be very special, because if you can define such a quantity, then A would need to always decrease along the cycle, but it would need to come back to the same point. So somehow it needs to be a sort of conformal manifold, but this A is in fact constant. So this condition really zooms in. Okay. But in fact, we can go even stronger. We can demand something even better. There's a strongest monotonicity, where this A mu that we defined isn't just any A mu, but is instead related to the beta function which governs this renormalization flow. So essentially, the beta function, which is a vector, will look like the gradient of this function A. And here, so for the entirety of this talk, we'll be working perturbatively, so we'll consider these to be some functions of our perturbative coupling. And in a second, I'll make more precise what I mean by this approximately symbol. It's not exactly the gradient, as we'll see. But what does this give you? Well, the A defined here is in fact a strongly monotonic function already. You can show just from writing down an expression like this that implies that A will monotonically decrease along the flow. But it in fact gives you a bit more. Gives you strong monotonicity. Plus, it gives you some constraints on the spectrum of operators in your theory. It guarantees that the dimensions of nearly marginal operators are real. So you get some real operator dimensions. And so it's the sort of strongest thing that you can demand. This is really the holy grail of these monotonicity theorems. If you can prove this sort of expression or a class of theories, then you have most monotonicity you could demand. And so that's, for the rest of the talk, will be focused on examining this sort of flow, which is also called gradient flow because the beta function is the gradient of a function. We'll focus on this in a specific class of theories. So before I get there, I have to say what I mean by this squiggle. So we'll say that a beta function will be gradient if it can be written in the form the derivative of, so if there exists A and a tensor Gij such that the derivative of A, where this derivative will be a derivative with respect to the couplings in our theory, is equal to the beta function up to some tensor G, where we want to restrict this tensor G must be symmetric and also positive definite. And you can ask why these conditions are important. You can ask what happens if you relax these conditions. Positive definiteness, this is really crucial. Positive definiteness is actually what gives us the monotonicity of this system. You can show that if you take a derivative of A with respect to this RG parameter mu, that this condition, this strong monotonicity condition on A, is equivalent to a positive definiteness of this tensor G. So this is what gives us strong monotonicity. And the symmetry condition is what gives us the extra stuff. It's what makes this true gradient flow. This is what gives us the real operator dimensions. You can show that if this tensor is symmetric, that's then the mixing matrix you get for these nearly marginal operators, which is related to the derivative of this beta function, is then also symmetric, which guarantees you the operator dimensions of your nearly marginal operators are real. So we'll want to demand that it's both symmetric and positive definite. And you notice then, these are exactly the same conditions you demand of a Riemannian metric, which is why I've sort of written the indices in this suggestive form where the G is almost lowering this index on B. But it seems like gradient flow naturally imposes some sort of Riemannian metric on your space of couplings. And this is defined throughout your entire space of couplings for all lambda. I mean, it's perturbative, but that's the only restriction. And really, we'll see that it must be that you can't just take it to be the delta function. The gradient flow really does give you this pair, this monotonic function and this metric. And part of the goal of the talk will be to figure out what this metric actually looks like in a specific class of theory. What are the questions that we want to ask? Well, first, I guess it's important to sort of prove that gradient flow is relevant in a certain class of theories. You can construct, I mean, here this expression is really, I try to write it in the most general form possible. There are these capital Latin indices, which can represent any sort of flavor indices you want in your theory. These can be defined for any couplings you want, so you could have any field content. But for simplicity, we'll focus on a specific class of theories. We'll focus on purely scalar theories with n massless scalar fields. So first is RG gradient for multiscalar models. I'll introduce more precisely in a second. And not to spoil things, but the answer is yes, you can write down a solution. You can find an A and a G that works for these models. And so secondly, what does G look like? That is to say, what does the sort of geometry that gradient flow imposes on the space of multiscalar theories look like? But first, to get there, we have to write down a solution. So these multiscalar models here will work in 4 dimensions and 4 minus epsilon dimensions. And because everything is perturbative, we want perturbative control over these RG flows. We are not going to use non-perturbative methods by any means. And this really restricts what type of Lagrangian we can write down. We can only have operators which are marginal in 4 dimensions. So we can just have, for interaction term, some quartic interaction polynomial in the fields, where these little indices are ON indices which run from 1 to n. And here this specifies for us what our capital indices are. So this capital index, we want to be the index that appears on our interaction tensor. And here you see what this is. So I will precisely be 4 of these vector indices bundled up in a symmetrized way. So each time you see one of these capital Latin indices, just remember that there are 4 of these normal ON indices hidden inside. And by no means are we the first people to study this problem of gradient flow in this system. It's actually a problem that's been studied since essentially the beginning of the epsilon expansion back in the early 70s. Wallace and Zia noticed that if you write down the beta function for this system with generic lambda, it's simply a fact that they noticed you could write it in this form. Basically, there existed a G and an A that worked. And then they noticed that this applied some monotonicity properties. And more recently, this was also studied. That work was in the 70s was through 3 loops. More recently, in 2018, Ian Jack and Colin Poole looked at this 1 loop order higher through 4 loops. But by now, the general beta function for these couplings has been written down through 6 loops. And so part of the goal here is to see if gradient flow still holds through 6 loops. And it's not just a sort of exercise in going to higher loop orders for its own sake. Because as we'll see, genuinely novel behavior arises in these beta functions beginning at 5 loops, and it's associated with asymmetrical wave function normalization graphs, and it's simply a sort of fact of graph theory that these only arise at 5 loops. And so part of the question is gradient flow spoiled at 5 loops above by this subtlety?
And here you don't care about whether this theory actually exists non-perturbatively.
No, this is all, yeah, it's all perturbative. I mean, we're interested in having access to Wilson-Fisher fixed points to study these flows perturbatively, but it is, yeah, it's all on the epsilon expansion. There's nothing non-perturbative. That's right. So as this is all perturbative, the goal will be basically to write down this expression in the most general way possible, cut it off at 6 loops and discard everything else and see if we can solve the resulting finite system of equations. So we can have to write down what the players in our game are. So we have A, we have G, and we have the beta function. The beta function is known its input. It's computed by the company and Panzer. This paper. But the indices on these various objects tell you what they're going to look like. So A has no indices. So any diagram you write down that's an A has to have all of its internal lines contracted. What will A look like? A will essentially be a sum of our vacuum diagrams with certain coefficients. These TIs, these are some vacuum diagram tensor structures. And so it'll look like something. 1 times the lowest order one you can have as just 2 lambdas with all the indices drawn together. Each vertex, I should say, in these graphs is a lambda. And then you can keep going. You can keep adding more vertices. There's other one next order. And so on and so forth. But this isn't connected to any sort of partition function or anything like that. These are arbitrary coefficients, and these will appear as unknowns that we want to solve for when we look at that expression. And similarly, G, what will G look like? Well, it has two of these indices, and these are each 4 indexes each, so we'll have 8 get grouped into 2 sides. So we'll have some sort of 4 to 4 scattering diagrams. And again, there's no connection between these and the actual Feynman diagrams in your theory. This is simply a sort of diagrammatic way of representing tensor structures. It's a tool keeping method, if you like. It makes things easier to keep track of.
Are we gonna be able to interpret capital A as like a number of degrees of freedom at the end of the day? Or
Yes, at the end of the day, so we'll see, we'll get a solution, and you can connect it to physical quantities that are supposed to be monotonic. There's a conjecture for a quantity in 4 minus epsilon dimensions. This F tilde, it's related to the log of the partition function, the sphere. But that requires a specific choice of these. So somewhere in your solution space, yes, you should be able to have this interpretation. So we have these various players in our game, and the beta function will just be the usual beta function with the normal coefficients. And all we need to do is just construct these equations. The derivative will just be a derivative with respect to the couplings. It'll remove one of these vertices in all the different possible ways from your diagrams. So you just take these diagrams, remove vertices, take the diagrams here, combine them with the diagrams in B, and then just match on either side. We'll get some expansion on the left-hand side and on the right-hand side, and the coefficients have to match. So you get some finite system of equations. And so to give you an example, an idea of what this looks like, we can sort of look through 2 loops. Through 2 loops, everything actually is trivial. Because the diagrams that appear in A will be some of these plus a few more. This is at sort of 0 loops. This is at 1 loop. There are 3 diagrams that appear at 2 loops, but in the interest of saving chalk, I won't write them down. But the point is that through 2 loops, if you look at these diagrams, they're very symmetric. No matter which vertex you remove, you end up getting the same diagram. So if we remove one of these 2 vertices here, this will just give us 1 vertex left. And then regardless of which vertex we remove here, we'll end up getting this sort of 1 loop bubble diagram. Which means on the left-hand side of this expression, each of these will get a contribution from one of the A's. And on the right-hand side, it'll be the same contribution just from the beta. So our equation for this will be something like A1, or maybe twice A1 is minus epsilon, whereas here comes from the classical term in the beta function. And then it'll be similarly some A2 is some coefficient. But you can see the point being, because they're so symmetric, there's a 1-to-1 correspondence between diagrams in the beta function and diagrams in A. So you can easily just solve this expression. It's linear in A, and it's but at 3 loops, this stops being the case. Things stop being so nice. And this is why you need to add the metric in. You see that it needs to be non-flat. You get a diagram, well, for instance, you get a diagram that looks like this. So this is a diagram in A at 3 loops. At 3 loops, the beta function will be order lambda to the 4. So the diagram will have 1 more lambda, it'll be order lambda 5. And you should get a diagram that looks something like this. And you see now that unlike in these cases, we have multiple ways of removing vertices. So we can remove one of these vertices, and we'll get some sort of propagator correction diagram that looks like this. Or alternatively, we can remove one of these vertices, and we will get some sort of diagram with disconnected divergences. Something that looks, I believe, like this. And similarly, this one will give us a third different graph. But they all come from the same contribution in A, so there'll be some A multiplying them. And on the left-hand side, the same A will appear in front of all of them, possibly with some symmetry factor associated with a number of different vertices that get the diagram and so forth. But then on the right-hand side, if we ignore G and we try to just solve beta is the derivative of some A, then we need to solve if A is some number over here, some number 1, A is number 2 over here, and the same A would have to absorb this other diagram as well. But if you look at these numbers, this turns out to be 0. This turns out to be -1/8. And the third one is -9/8. And clearly these are not all solvable. You cannot choose an A or choose one of these big A such that its derivative is just the beta function beginning at 3 loops. This is what Wallace and Zia found back in the 70s. You add back this G. What that means is you add in extra diagrams on the right-hand side. You contract this with some terms in the beta function. So you'll get plus some G's over here. And these come in and save the day, and you can find the solution. The equations end up being full rank at the cost of introducing this metric. So
This metric has a network interpretation as 2-point functions of the potential terms.
Yes, I'll get to that in a minute. You can give it that interpretation. In general, I mean, the solution space is larger. But there is a point in the solution space which has its nice interpretation. So you can ask what happens at higher loops. So at 3 loops, adding back the metric is in fact sufficient to make the system of equations you get full rank. So a solution actually will always exist regardless of what the particular coefficients of the beta function are. And you can ask if this continues at higher loop order. But you can see that something must happen, because if you look at the number of unknowns you'll have in these equations, what unknowns will you have? Well, the number of unknowns will basically be just the number of vacuum diagrams you have at a certain order, plus the number of 4-to-4 scattering diagrams. And the number of equations you need to solve will be equal to the number of beta function diagrams you have. So just sort of full vertex diagrams. And if you look at the loop order, you see that as the loop order increases, the number of equations grows much more rapidly than the number of unknowns you have to solve. So at low loop orders, everything looks nice. You have more unknowns than you have equations, but then things begin to pick up. And sorry, I numbered my loop orders off by 1. And by 6 loops, by the highest order that we want to look at, you have 819 equations, and you have to solve all those equations with only about 600 different unknowns. And the number of unknowns you get that remain unfixed from lower orders isn't enough to make this number match. You see, the number of equations will be bigger than the number of unknowns. If there is a solution, something must be up. There must be some accidental redundancy in these equations. And this is exactly what you find. In the end, you try to solve as many of these equations as you can with the unknowns that you have. And what you're left with once you've used up all this freedom is some equations which depend only on the beta function coefficients that appear. And so these are constraints on the beta function, which must be satisfied if a solution is to exist.
Is it the integrability conditions? Just from that is a gradient, so you can take derivatives with respect to I and j, and then it has to be independent of order.
This I don't know. Actually, that's an interesting.
But you have those constraint beta function for the solution to exist, right? Just dij.
I don't know if those are all of the constraints that you get. Certainly those should be constraints, but I don't know if those are the entire class. So the constraints, this is what was previously found by Jack and Poole. Jack and Poole looked up through 4 loops. They found that there were 4 constraints that appeared. So as soon as you go 1 loop order higher than what Wallace and Zia looked at, you sort of run into these problems. The beta function can no longer be general. And we find through 5 and 6 loops that the existence of a solution is predicated on about 300 other constraints. Now, some of these constraints are easy to understand. For instance, there's if the beta function at 5 loops will contain basically these 2 diagrams, which I will try to draw. The beta function at 5 loops will contain these 2 diagrams, and you find that one of the constraints, one of these 41, is just that this coefficient is equal to this coefficient. And in fact, they are both equal. They're both equal to 36 zeta 3 squared. So the constraint is indeed satisfied. And you can actually, just by looking at the diagrammatics, figure out where this constraint comes from. So these are both primitive diagrams. You see that all the vertices are connected by a minus 1 line, so they have no subdivergences, which is why these 2 coefficients are schema invariant on their own. And in fact, they're sort of special because they both come from the same contribution in A. If you look at taking an extra vertex, sort of from infinity, and adding it back on and connecting it to the 4 loops, to the 4 legs, sorry, you see that they basically both come from the same contribution in A. This one vacuum diagram, which looks like this. And depending on which of the vertices you remove, you'll get one of these 2. I believe if you remove one of the 3 internal, 3 sort of in the middle, you'll end up with this one. And if you remove one of the 4 on the outside, you'll end up with this one. But the point is,
It's resolved in the middle. You have a sextate coupling here. No, that diagram, multiplying B1.
this, so no, there's no vertex
Okay.
here. This is just, it's like,
It's on top of it, yeah.
yeah, they're all on top.
But it's missing a line, right? Because there's some 3 point. It's fine.
This,
Your 4 point, right?
No, but the one next to that one is 3 point. It's fine, but in the B one, it's fine.
Yeah, I think the way you have,
That's
yeah,
this
the
one.
way.
Yes.
Yeah.
this one, yeah, there's an extra line. Sorry, that's right. There's an extra line like this. That'll be the extra.
Yeah, there are 2 3 points.
Yeah. But the point is, so you go back to the original equation. So the original equation, remember, we want a derivative of this A to be G times beta. And you can think about this right-hand side as sort of a forest structure for your normalization. So you have different ways of contracting subdivergences, and that's captured by the different terms in here. But for these diagrams, there are no subdivergences. So the only way to sort of shrink this down is to shrink the entire diagram, which means that the only contribution on the right-hand side will just be this B1 and B2. But on the left-hand side, they have to both be absorbed by the same A. So there was, at 2 loops, there was a 1-to-1 correspondence. That's what allowed us to solve things trivially. But here, there's sort of a 1A has to absorb 2 Bs, and no metric can compensate it. So I guess in the end, you get some A equals B1 and A equals B2. And this must both be satisfied. So clearly B1 must be equal to B2, which is what you find. And in fact, you can ask, does this hold for all primitive diagrams that have the same completion, so that they get completed to the same vacuum bubble when you add an extra vertex in? And in fact, it does. And incidentally, independently, it's known from the amplitudes community who study these types of primitive diagrams that the coefficients of the Feynman periods of these diagrams are actually related in such a way. So any of these, the sort of primitive type constraints that come from two primitive diagrams with the same completion must be satisfied at all loop orders. It's known from that there's a proof from the amplitudes community. But not all of the constraints are so nice. A lot of them are a lot more complicated. There are some constraints at 6 loops that involve hundreds of these beta function coefficients, and they're quartic in the coefficients, or they involve various orders. And so presumably there is also some amplitudes reason that they're satisfied, but it's much less clear than this nice clean interpretation. It's much less clear how to generate them in terms of amplitudes terms. And it's less clear why they are satisfied. I should say all the constraints you get, the gradient flow, the existence of gradient flow is a sort of physical statement you make about your system. But the beta function itself is not a physical object. It is scheme invariant, and the coefficients of the beta function change depending on the renormalization scheme you calculate them in. The scheme we use, the results we use are calculated specifically in the MS-Bar scheme. But this particular scheme shouldn't matter because it's a physical statement. And in fact, you look at all these constraints you get, all of these 315, and you find that you change the different coefficients, and the scheme change cancels out. They're all, even though the coefficients inside them change, the overall equation is scheme independent, which means that it is really a physical statement. If all these expressions are satisfied, then there does genuinely exist a solution for gradient flow. So you can ask, are they all satisfied? You can plug in the solution, and you find that out of the 315 constraints, 310 are satisfied. Now, this is sort of very peculiar. I don't know, maybe it's just me, but I would expect that if gradient flow doesn't work, if you can't find a solution, that it should sort of explode. It should really not work. It shouldn't sort of whimper. There shouldn't be just 5 of these constraints which aren't satisfied. And they're not the most complicated by any means. They're sort of average constraints. So it seems a bit confusing. And so you scratch your head for a bit, and then you realize that, in fact, the question we've been asking this entire time is sort of incorrect. Because beginning at 5 loops, the object which appears in the trace of the stress tensor, so the thing that really sort of governs whether or not a theory is conformal, and so governs our G flows, is no longer this beta function that you sort of naively compute by renormalizing the full point function, but is instead this B function, where B is essentially the beta function plus its extra contribution called S, where S has 2 of these ON vector indices and is anti-symmetric. And this is what I was saying before. There's a subtlety associated with asymmetrical wave function normalization diagrams. This is exactly that subtlety. You see that because it has 2 free indices, it must look something like this. It has to have 2 free legs. And because it's anti-symmetric, whatever this bubble is has to not be symmetric. And it's simply, you just write down all the possible graphs you can in 5-4-3, and such graphs only begin to appear at 5 loops. That's why at 5 loops you begin to have this problem. This S, there's a prescription for how you calculate it. It's very specific. It's a specific object you calculate, and you have to tack it on to the beta function to get this sort of physical B. So the question now is, if beta is not gradient because there are these 5 constraints that aren't satisfied, is B gradient? And the answer, in fact, is maybe. We don't know.
And sorry, the B cannot be just the beta function in different scheme.
It's the ambiguity that means that you need to shift by S isn't exactly a scheme change. It's more associated with
It cannot be integrated to a change of.
no. It cannot. It's more associated with an ambiguity associated with wave function, with field redefinitions. That in fact the beta function is it's usually defined as ambiguous, but this object isn't, and that's but it's not a scheme change.
But so this definition says that B transform in a specific way. I mean, what do you mean? I mean, the
So-
beta function is ambiguous. You're saying the capital B is not ambiguous? I mean,
Yeah,
it's
so
ambiguous up to a change of.
The ambiguity
Yeah.
is essentially if you can always redefine your fields by
Yeah.
some sort of ON rotation.
Yeah.
So you can rotate them to some new fields.
Mhm.
But the problem is that usually what you compute in renormalization is to renormalize the fields, you compute the 2-point function.
Mhm.
But the bare fields are related to the renormalized fields by some z phi to the 1/2. So the 2-point function computes z phi to the 1/2 squared.
Mhm.
You can rotate the fields. This will rotate this without changing
Yeah.
the 2-point function. And you can introduce extra poles, and that's an ambiguity in beta, but it's an ambiguity that's cancelled in S. There's this is figured out by I think he was born in when they looked at the A theorem and 4 dimensions, and there's a specific way to compute the S such that this is not ambiguous.
Is this keeping track of some kind of non-trivial curvature for the internal ON bundle?
Yes, it is. Yeah.
I see.
Yeah, you want the objects basically to be gauge invariant, but it
Yeah.
turns out that beta is not gauge invariant, but S is not gauge invariant in exactly the opposite way.
I see.
So B is gauge invariant. That's the So is B gradient? So we take the 5 constraints. Well, we take all of our 315 constraints. We find that the ones that are satisfied are still satisfied for B. Basically, they're the ones that involve coefficients that aren't shifted by this change beta to B, that are not affected by this S. But the remaining 5 that aren't satisfied become 4 constraints on the coefficients that appear in S. So there are 4 diagrams. They can appear in S at 5 loops. There's 4 asymmetrical wave function normalization graphs you can write down, and there are an additional 19 at 6 loops. And so the 315 constraints become 4 constraints on S. I won't write down all of the constraints. I'll just highlight 2 of them. 2 of them only involve the 5 loop S. So there's some, say S1. One of them actually fixes the values of one of the coefficients, some number, some 259 over 4608. And this is the coefficient of the diagram that looks like some complicated diagram that looks like this. And you can see it's not symmetrical. If you flip this, it changes, but its coefficient has to be fixed. And then there's some other 1, 2 plus 3, 84, yes, 3, some 31 minus 36, zeta 3. Well, these are 2 of the other diagrams that appear at 5 loops, but it's not this. Now, after we published this paper, Giombi went out and computed this S. It's some sort of complicated expression. You have to make your interaction vertex depend on space-time, and so it's not just as simple as computing this as you normally would. And in fact, they found that these 2 constraints were satisfied. They compute S through 5 loops. So 2 of the 4 are good, but the other 2 we don't know. The other 2 involve constraint coefficients on S at 6 loops, and this just simply hasn't been computed. But I would say that given the fact that basically we had to go through 313 nasty constraints, I would bet that if you actually do this horrible computation through 6 loops, the remaining 2 would also be satisfied. And
Yeah, go ahead.
Was, so I would expect B should be gradient, not beta. What do you?
Yeah, so I was just gonna mention, so perhaps we also expect constraints on, I mean, the fact that the components of S are not independent. Maybe that's also why. Like. I mean, because if S were to have the interpretation as the curvature for this normal ON directions, it will have to satisfy constraints coming from, say, Bianchi and Lindsay. So maybe not all the, the individual, like coefficient you would have for S are independent. And then, these constraints will be more than, I mean, closer to, fixing everything.
That's true. That is a good point. We haven't looked at these Bianchi identities, but it's possible that they, yeah, it's possible that these are related to those, certainly. But they verified these expressions by explicitly computing S through 35 beliefs.
Wow.
So the moral of the story of this part is that B seems to be gradient. We had to go through 310 constraints, which were automatically satisfied, and these were the constraints that just involved the terms in B, and then 2 more of the constraints on S were satisfied. So it seems pretty, let's say, convincing that B should be gradient, not just through 6 loops, but also you would expect this to continue to occur at higher loop orders. I mean, you would just have to solve more equations with more unknowns. Things would just become more complicated. But what's interesting is that the only input really is graph theory. The only input in these constraints is just graphical. All you've really told the system to get these constraints here, you haven't even imposed what the beta function is. All you've said is that the graphs must be constructed from 4 valency vertices. So they just have to have these. All vertices must have 4 lines going in and out of them. And somehow that is enough to drive all these fairly nasty constraints on the beta function, which seem to be satisfied. So it seems like the graph theory is telling you something, the amplitudes, but we don't know exactly. We don't have a proof like there is for these primitive constraints why other constraints can be satisfied. Some of them are not all that more complicated than these. They're still linear. They just involve more of the constraints. But we're working on that at the moment. Now, we have a solution. So what does it mean? We have a solution. We've written down an A and a G, but it's sort of the most general possible thing. And in fact, there's a lot of redundancy involved. Even though you've used all the freedom you can to get these constraints, there's still extra freedom that remains in A and G. It sort of, it doesn't just happens to, the coefficients don't all appear independently, which means that there's some sort of solution space. And so usually when we're looking at monotonicity theorems with the A theorem and the C theorem, what you're interested in isn't just the existence of a solution, but in attaching a particular physical observable to this A. So the question then becomes, is there a point in the solution space where you can do this? And the answer is yes. So there's this. We're here. The tricky part is that we're not working in the integer dimension. We're working in 4 minus epsilon, because there is where we have access to these perturbative Wilson-Fisher fixed points. And so we can't match to the A theorem or the F theorem. But there's this conjecture that there should be this object in between dimensions, in 4 minus epsilon dimensions, F tilde, which should interpolate between the F of the F theorem in 3 dimensions and the A of the A theorem. And in fact, I believe it should also interpolate with C and so on. And this F tilde is defined similarly to how F is. It's defined as the log of the partition function on SD, but there's this extra dimension-dependent prefactor, which ends up just soaking up a divergence in 4 dimensions to get A.
It'll give you alternating signs when you jump back to.
Right. So this is how it's defined. And there's some perturbative evidence. People have looked at this object, evaluating it at these various Wilson-Fisher fixed points, and they find perturbative evidence that it's weakly monotonic. So in the IR, it's always lower than in the UV. And in fact, we can choose some of the coefficients that are unfixed, such that F is a multiple of our A, evaluated at any of the fixed points that you like. So A is defined for any coupling, but this F only exists at certain discrete values for these couplings. If you go to these couplings up to some overall rescaling, which doesn't really matter, you can just rescale both sides of this equation and the scaling sort of drops out. You find that this A becomes the F. What's nice about this is that our A is defined beyond just the fixed points. And so it seems like this F tilde theorem isn't just a weakly monotonic theorem, but a true full gradient flow theorem, even away from the fixed point. To get this matching, so the people who look at these things, they write down F through 3 loops. I believe in through 3 loops, there are 3 unfixed coefficients in the A that we can use. 2 of them are used up in matching A to F, so we still have 1, but we still have another object, we still have this G. And so what does that become? And in fact, you can use the extra degree of freedom to match Gij to the 2-point function coefficient of these nearly marginal operators in your theory. So you get this nice sort of expression that's sort of reminiscent of the C theorem, where the derivative of this monotonic function is equal, now it's B, the beta function, up to some 2-point function coefficient, where away from the fixed points is defined using our G. Now, that's nice, but we still don't really know what G is, even at this fixed point. And as I said before, just from the way we construct it, it has to be symmetric and positive definite. It looks like a Riemannian metric. So what sort of metric is it? Now, there are a lot of ways of investigating this question. There are a lot of ways of characterizing manifolds. And we just really pursue the most basic question by looking at what the Ricci scalar is associated with this metric G. So the Ricci scalar, everything is perturbative in this game. So the Ricci scalar 2 will have some expansion from some tensor structures. Again, it'll have an expansion like A. It has no free indices, so it'll be an expansion over vacuum bubble diagrams. So it'll have some constant term plus some linear in lambda plus some. And we can compute these coefficients here just by taking the explicit expression for G. So Riemann tensor will involve 2 derivatives on G. So to get through order lambda in the Ricci scalar, we'll need the order lambda cubed in the metric. And you simply just have to take derivatives and see what you get for these coefficients. So I'll have the usual expression in terms of the Christoffel symbols. But the tricky thing here is that all of the indices that appear aren't just the usual ON vector indices, these generalized indices. So they disguise 4 symmetrized little indices. So each of these contractions really is secretly 24 different terms. And so you can see there are 6 contractions. Writing out these things explicitly in terms of the lambda tensors involves a few billion terms. You can put them on the computer, but it takes a few days to chug through, but you can do it on the computer. But in fact, you can do it more quickly by hand using diagrammatics. Because what will the terms look like? Well, we're contracting these generalized indices. So we'll get factors of n. And essentially, these things will really just be combinatorial factors associated with the different loops in these indices. And these combinatorial factors can be most naturally characterized diagrammatically. So for instance, we can look at just this first term and compute its contribution to the constant term in the Ricci scalar explicitly. As an example. So the Christoffel symbol, this will involve just one derivative on the metric, and to refresh your memory, the metric at order 1 will just be some coefficient times this diagram. We need to take a derivative of this diagram, so we remove this vertex, we sort of open it up, which means that the Christoffel symbol at order 0 will just be this sort of triangular diagram with 3 sides and an index attached to each side. And what we need to do to find this term is we need to first take an internal contraction of this Christoffel symbol and then contract 2 of them together. And you can think of sort of physically bending the diagram and connecting the lines. But here there's an implicit symmetrization. There's an implicit symmetrization over these the 4 different lines that appear at each edge. So you have to connect the lines in all the different possible ways and then count the loops that appear to get the n-dependent combinatorial factor will end up. Yeah. So what does that look like? If we contract a top index with a bottom index, we can sort of bend this over, and you'll see we'll get this a diagram that sort of looks like this. So we'll have still a free index at the top, and then in the middle, we'll be doing a contraction. We want to connect each of the legs up in all the different possible ways. It just involves counting loops. And if you do this, you find that at the end of the day, there are 2 ways of getting 2 loops. And that will give a factor of n squared. I believe there are 10 ways of getting 1 loop, and there are 12 ways of getting no loops, 1 by 24. And in the end, no matter what you do, the resulting diagram will contract the 4 free indices into 2 pairs. So we have the combinatorial factor, then we just need to take 2 of these together, smush them together again, count loops, and in the end, you find some n-dependent polynomial, which will be your contribution. And that's only one of the terms. There are 3 others, and they become slightly more complicated, but this is the sort of game that you play, take derivatives, remove vertices, sort of combine them together, count loops. And in the end, you find some sort of complicated expression for the Ricci scalar, which has a few features of interest. Unfortunately, so the matching that we performed between the metric and the 2-point function was only at leading order in the 2-point function coefficient, and so we didn't fix all of the coefficients that appear in our solution, and namely, we don't fix all the coefficients that appear in the Ricci scalar. So the Ricci scalar isn't completely determined, even at a constant order, and it's more unfixed coefficients appear in the order lambda 1 coefficient. But in fact, at large n, the contribution is fixed, and it's fixed to be positive. So the constant term in the Ricci scalar, which is really the Ricci scalar, the curvature evaluated at the free theory itself, looks something like this. 6 epsilon and 7 plus 6 epsilon squared. And you can see that this is positive, and this is also positive for all positive epsilon. And the interpretation isn't clear what this positive curvature means, but the only input for the metric really has just been the beta function and matching with the 2-point function coefficient. And so somehow this positive curvature should capture some information about renormalization in the region of the free theory. Now, as I said, the value of the order lambda term in the Ricci scalar can be determined. It involves, to determine it, you'd have to match with the two-point function coefficient at higher order, which we haven't been able to do. But whatever it is, you can still actually figure out something interesting. It'll be some polynomial in n, some polynomial in n and epsilon, times the only tensor structure which appears at order lambda, the only vacuum diagram you can write down. This one, you take one interaction tensor and can just take two traces. And the interesting thing about this is that this is bounded for all fixed points to be less than or equal to the value at the ON point. And so we can't determine the sign of this polynomial for n or epsilon, but it seems like amongst the fixed points, the ON fixed point extremizes the curvature. We don't know if it's minimal or maximal, but it certainly extremizes this curvature.
And that you can interpret because of the enhanced symmetry.
That is the interpretation, but it's
Because typically-
this bound comes from enhanced symmetry. Yeah. But yes. So where does that leave us? So to sort of remind you where we've been. Through 6 loops, we can write down a solution to the gradient flow equation. There exists a solution through 6 loops. The solution is not general, but one point in the solution space can be given a nice physical interpretation in terms of this F theorem, F tilde theorem, when matching with the two-point function coefficient. And here, this really should be B. And then at this point, the metric is distinctly curved. So the space of theory seems to genuinely be curved, and namely, it's positively curved at the free theory. And it seems to be an extremal curvature at the ON fixed point. And so it seems like the space of theories naturally has some sort of sense of curvature, capturing somehow RG information through this metric defined through gradient flow, and also through the two-point function coefficient. Now, this was only done for multiscalar models. You could consider what happens in more general theories. This expression really is quite general. You could increase the number of couplings you have. Now your generalized index wouldn't just be this IJKL. It could include some Yukawa coupling, for instance, gauge theories. You can still write down this expression perturbatively. They have some finite number of diagrams you write down. You can still do this matching. So you could try to investigate gradient flow in other systems and find this metric in more general gauge from your own scalar systems. And people have previously studied a similar expression in those cases, not with a symmetric G, but with an asymmetric G. It was proven by Jack and Osborne in the 90s that a solution to this always exists. That you can use the fact that a solution exists to derive these constraints on the coefficients in the P function, and you know that they have to be satisfied because the solution exists. So there's also interesting to look at the amplitudes interpretation of these constraints, trying to construct something similar to what there was for the primitive graphs, but now for more complicated graphs. And this is, people in the amplitudes community really restrict themselves to primitive graphs because they're by far the easiest to deal with. Not that much is known at high loop orders about how these non-primitive graphs behave, but these constraints give you some sort of information.
But what is the physical interpretation in the antisymmetric case? What is the physical interpretation of this equation?
Well, because
all the quantities that show up in this equation.
So this A and becomes the A of it's the A theorem, it's the A anomaly. The symmetry isn't responsible for the monotonicity. So as long as this is positive definite, it can be asymmetric.
Okay. It's still positive definite.
Right. So this is If this isn't symmetric, then you get just strong monotonicity, not gradient
Okay,
flow.
okay.
And you still get constraints. You don't get as many constraints because you have more freedom in the metric to solve. But you know those constraints have to be satisfied. And finally, it'll be interesting to try to understand more deeply how this Ricci scalar really captures RG information, how the geometry encodes renormalization, what this positive curvature really means, and figure out more about the space of theories perturbatively. Thank you.
This E, how does it transform under a change of scheme?
It transforms, you can think of a change of scheme in the sort of differential language as a diffeomorphism. So a change of scheme can be realized by shifting your coordinates like you would a diffeomorphism to some lambda prime. And then B will transform like a vector field. So B and beta will both go to a B prime, which is lambda I prime. Will just transform like a vector field. And then what you can do, this will have some, to figure out how the coefficients transform. This will have some expansion in terms of some coefficients and some tensor structures in terms of the lambda prime. This, you can write down what lambda prime is in terms of lambda. It will be some different tensor structures, and you can transform everything to be in terms of lambda, match both sides, and then you'll find how to relate the scheme changed coefficients, the original coefficients.
So in the case of one coordinate, one lambda, right, you can use a definition to essentially eliminate all the higher loops. If the first
Yes.
coefficient of the first two, right?
Yes.
And the rest you can set to 0.
Yes.
In a scheme. So here, what can you do when you have n coupling constants?
You can't set all of them to 0. Certainly the primitive diagrams, no horns and no subdivergences, these will be scheme invariant. The coefficients you won't change under this scheme. You can set certainly set some to 0. You can try to choose a nice scheme where most to 0. But the easiest way in terms of this gradient flow is to really not work with specific coefficients, but leave the coefficients general, and then get these constraints, and then you can show these constraints don't change under this scheme. That's the easiest way to think about this, the existence. That makes sense. For the case of one coupling, this expression is sort of trivial because for one polynomial, you can just integrate it explicitly to find some function A. So for the ON model, for instance, with one coupling, it will always be gradient. You can write down technically what this A is.
Is it understood what's happening in theory space when your curvature diverges?
No, that is a good question. I guess you can ask, do those points coincide with the fixed points? And it doesn't seem like it. I guess perhaps it would be sort of, it probably sort of violates with an assumption we have made in writing down this metric that it's perturbative. It would certainly probably violate this positive definiteness condition, because the positive definiteness really comes from basically the metric starts like just the flat metric plus some order lambda corrections. And if these start to compete with this, you sort of lose the interpretation in terms of gradient flow. You sort of probably lose perturbative control as well. So
Not perturbatively can happen, the curvature diverges. Just take compact boson, take a large radius limit, the curvature diverges. Also happens in more non-trivial example, like so-called conical singularities or Clavier sigma models, but it doesn't rise in the perturbative set. The CFT will become singular because the fraction becomes dense. I have a related question. So here, do you expect there to be like two-sided bounds on the curvature coming from the OM model and from the symmetry from the Gaussian model?
Yes, I guess there should be, if this function has a definite sign at a
Yeah.
particular n and epsilon,
Yeah,
then certainly. This should always be positive for any,
Yeah.
you can show that this has to be positive for any. Fixed point, and so it should be, I guess, bounded. Well, this is,
depending on the sign. Yeah,
depending on the sign,
yeah,
the free theory will also be.
Yeah.
Yes.
yeah.
Yeah, so they are the points of sort of symmetry and answer.
Mhm, mhm.
Sorry, maybe you said it. How unique is G?
It's
Geometric.
in the general solution, it's not unique at all. There are a lot of unfixed coefficients. It grows with the loop order. But it seems like the matching of G to this 2-point function coefficient is unique. At least in the loop orders we've looked at, it uses up all of the freedom. We haven't looked at high loop order, but we expect it to be a unique point in this solution space.
People looked for, it's a bit different, but have people looked for, because there's a nice graphical representation of this, so I was wondering if people looked for, non-trivial differential forms, like calculating the homology on the couple manifold.
This I don't know. This I don't know. But the G isn't defined just as a conformal manifold. It's defined really in all of theory.
I know, sorry, not the couple manifold, building a theory space.
Yeah, yeah.
Seeing the topology of the theory space, that's what I'm asking.
I don't think people have computed this, no, but it'd be a very interesting thing to look at. To try
Because
to,
the graphic calculation seems to be.
try to find the global properties.
Yeah,
of
that's
the
right,
space of
that's
two
right.
bases. Yes, certainly. Yeah, there are many more things you could look at beyond just the Ricci scalar. You can look at sectional curvature and those
Yeah,
things.
Yeah,
And the holonomy.
And yeah, holonomy, yeah, certainly.
So that can be done with perturbatively.
yeah.
Yeah.
Do you expect the manifold to be this, this theory space, this metric to define some Einstein metric, or
Yeah.
any extra information do you have apart from positive curvature?
Really no more extra information. It's it's the limit of a. I know I'm very interested in trying to figure out more, but it's not clear if there's some dynamics or some Einstein equation or something like that.
And if people ask you what happens to the theory space, say in 3 dimensions, what do you say? How much of the structure would remain? There's the theory space for all the scalars in 3 dimensions.
But with 5 to the 6 interaction.
What about the 5 to the 4, the number of?
So only the relevant difference.
Yeah, you can still talk about the theory space.
Yeah.
What kind of the structure that you have
That's a
given
good-
here will remain?
That's a good question. I don't think it's clear. I think it's clear, especially because really we only have explicit expressions for R and G are very low.
Yeah.
It's not really for what
All these ingredients will change very much, but perhaps some of the structure, the constraints, the equation really came down.
Yeah, very possibly. It's we have. It'd be interesting.
Any more questions for William? If not, let's thank you.